Hello Stat 323 class, my name is Bo McAndrew and today I'm going to show you guys about a split plot design structure. To keep it simple, a split plot design structure requires a factorial treatment structure in which you block by one of the factors rather than a separate blocking variable that we like in a random complete block design. Some of the key features of a split plot design structure is that there's more than one experimental unit. Like I said, it's factorial in which there's multiple. And with this, what makes it a split plot design structure is that there is more than one randomization between the factorials. For our factors, we have a whole plot factor, which acts as blocks for our split plot factor, which is the experimental units in this type of design. Now we're going to look at how split plot design differs from a complete random design or randomized complete block design. Technically, you can use either of these in this type of design, and it'll depend on how you randomize your factors, because you can use blocking on top of the separate blocking variable of the explanatory variable, which I'll explain in a minute. The split also restricts randomization, which differs from a complete random design, as there are multiple combinations are applied, but they are all separated. And then also, as I mentioned earlier, it blocks on the explanatory variable and not a separate blocking variable, which is different from RCBD. Split plot designs derive from agricultural processes, and in the textbook there is a really good example that helped me understand how a split plot design works. I'll show you this example now. So they wanted to test the effect of 3 different irrigation levels and 4 corn varieties on their corn yield. But the problem was irrigation is so large that it needed to be widely spread out throughout the property. And this made it tough to make multiple samples of it just because of how large the space is for each irrigation. Using this example, I'm going to show you a model of how to create a split plot design. So basically, you have to come up with a whole factor. In this case, it is our irrigation because it needs to be wide and spread out. So with this, we are going to divide our land into 6 plots. And then we will randomly assign the irrigation levels to 2 plots. So therefore, we're getting a replication of twice, right, with this. So we'll just do it random. Irrigation 3, irrigation 1, irrigation 3, irrigation 2, irrigation 2, and irrigation 1. Okay, now we have to assign all 4 corn varieties to the each of the levels. So I'll split it into 4. Okay, I'm not going to do this for all of them, but I'll show you real quick. So we go variety 1, variety 2, variety 3, variety 4, just completely random. 1, 3, 2, 4, and so on until you filled it all up. Now I've randomly assigned all the varieties to each of the irrigation blocks. And now you will run your design with this process. This corn example is easier for me to see, at least, just because you can just envision the separate plots of land being the separate whole plot factors. After applying our treatments and running the experiment, now it is time to do our analysis. For our analysis, we use this model. In this model, we have that is the mean plus the effect of the whole plot level, plus the whole plot random error, plus the effect of the split plot factor, plus the effect of the interaction of the 2 factors, and then plus the split plot random error. Also, we have our ANOVA table and with our sources and degrees of freedom. I will go through it with you guys and show you how we fill it out for this example. So first we have our blocks replicated, which is S minus 1. We are replicated twice, so therefore our degrees of freedom for this would be 1. Okay, and then for factor A, we have the number of factors minus 1, so that would be our 4 minus 1 equals 3. Okay, and then it's 3, we only had 3, so 3 minus 1 is 2. Next we have our whole plot air, which is this degrees of freedom of the blocks replicated times our factor. So we get another 2 for that. And then now we have our second factor, which is the split plot factor. And this one is our corn varieties, which is 4. So 4 minus 1, we get 3 degrees of freedom for this guy. And then now we have our interaction source. With that, we do our first whole plot factor times our split plot factor. So we go 2 times 3 equals 6. And then finally our split plot air, which is our whole plot factors times our split plot factors minus 1 times our replication minus 1. So that would be a 3 times 3 times 1 is 9. And then finally we have our total, which is the number of experimental units minus 1, which is 23. All of this adds up to 23. So with our ANOVA table and our degrees of freedom, basically you compute the sum of the squares and the estimate of the treatment effects is in the same usual way that you would with other experiments. So yeah, that's how you do a split plot design structure and the analysis of it. I'll leave you with a few final thoughts to remember. To know if your design structure is split plot, you must know how the process of randomization occurred, because it has to start with that whole plot factor getting randomized into each plot, and then the separate split plot factors being randomized within those. So you won't be able to know the difference between nesting or other types unless you know that each one was randomized separately. So 2 randomizations. And then also with this, it is possible for multiple whole factors. With our corn example, that could be high quality dirt versus low quality dirt, and then you create separate plots with that. And then also for multiple split plot factors, you could do, we had corn varieties, so it could be like the red corn versus yellow corn on top of the other corn varieties we have, because red corn is rare, but it's a thing. So, yep, that was how to do split plot design. Thank you for watching. I hope you learned as much as you possibly could.